Ladies and gentlemen, this is your well-rounded math teacher, Mr. Bakar. We're on the last video in Unit 3, that is linear programming. And your learning target is I can create and analyze a linear programming model to solve a real-world problem. That's the last problem we're going to do. Just to talk about linear programming, many real-life problems involving a process called optimization. Right there. Finding the minimum or maximum value of something. For example, a company may want to maximize its profits. A farmer may want to maximize his income or his harvest by managing his crops using linear programming. So that's what we're dealing with. Minimums and maximums. A linear programming model consists of a system of constraints. This is your system of constraints right here, your inequalities, basically. And a system of constraints, which is your linear inequalities, and an objective function. I call this the minimum or maximum function. You're going to plug in some ordered pairs into this minimum maximum function, and it's going to give you your minimum or maximum. Solving a linear programming problem, finding minimum maximum of objectives. First, you're going to graph your constraints. Your constraints are your inequalities. Here it's y is greater than or equal to 2, when you're talking about just one variable y, that's this line right here, and it's greater than or equal to 2, so I would shade above it. And then you have your other two inequalities. Evidently we shade below this one and above this one. This shaded in area here is called your feasible region. Your feasible region is all your different solutions, but what they found with linear programming is your minimums and maximums occur at the vertices. So once we graph this and find our feasible region, we're actually looking for the vertices. It says right here, find the vertices of the graph of the constraint system, evaluate the objective quantity in the of each vertex. Basically, you're going to plug your vertices into the minimum maximum function. What a minimum maximum function or objective function looks like is this. You guys are used to working with f of x. This is f comma y. You're going to plug in two numbers, an x and a y value. So I'll just make up a minimum maximum function here. I'm going to say 5x minus y. So we have our constraints and we have it graphed. This is our feasible region. I'm going to pick a point on there. I'm going to pick this point right here. That point is 1, 2, 3, 4, 5, 6, 1, 2. This point right here, sorry, is 6, 2. If I plug that into my minimum maximum function, I'd be finding f of 6 comma 2. So I'm going to plug in 6 for the x right here and 2 for the y right here. So what it ends up being is 5 times 6 minus the 2, or 30 minus 2, or 28. Now that might be a minimum, maximum, or neither. We would have to plug in these other vertices into what we call an objective function. So it's kind of a little bit of an example of what we're doing. Let's do a full-blown example here. Okay. Graph the following system of inequalities. Name the coordinates of the vertices of the feasible region. Find the maximum and minimum values for the function. So here's our objective function. You can see f of x, y. We're not going to graph this. We're going to use this in a little bit. This is where we plug our vertices into this minimum maximum function. Here's our constraints right here. There's 3 of them. So we're going to have 3 lines. Our feasible region is going to be a triangle. I'm going to graph this first one in blue. X is greater than or equal to 1. When you're working with one variable and it's x, it's a vertical line. So I count over to 1. There's my x-intercept of 1. And here's my line. You want nice straight lines. You probably should use a ruler for this. I'm not going to. I'm just going to kind of show you what's going on. Now, it also says it's x is greater than or equal to 1. So we want values of x. We got to shade one side or the other here. We want values of x that are greater than 1. Well, it's pretty easy when it's a vertical or horizontal line. 2, 3, 4, all these are bigger than x. So I know I'm going to shade this area. So I'm going to draw a little arrow there to show that I'm going to shade that side. Y is greater than or equal to 0. Okay. Y, you're talking about horizontal lines. First of all, I don't have an x-intercept, but I do have a y-intercept. My y-intercept is 0, and it's a horizontal line. Okay? It's greater than, again, now with y, working vertically here, down would be negative, up would be positive, so we're going to shade above it. 1, 2, 3, these are all greater than 0, so we shade above. This last one here, two variables here. I'm going to solve for y, so I'm going to subtract 2x from both sides. And I'm going to get y is less than or equal to negative 2x plus 6. Graphing this, I have a y-intercept of 6 right here. My slope is negative 2 over 1. So down a negative 2 over a positive 1. Just because your slope is negative doesn't mean both movements are negative. So down 1, 2 over 1. Down 1, 2 over 1. Down 1, 2 over 1. I can see my vertices right now. Okay. Once again, it's less than or equal to, so this is a solid line. Now I got to see which way I shade. It looks like the triangle, it should be the inside, but just to make sure, you're going to use a checkpoint of 0, 0. So I'm going to plug in 0 for y is less than or equal to negative 2 times 0 plus 6. So this is 0 is less than or equal to 6, basically. Is 0 less than 6? This is true. Here's 0, 0, that point we just plugged in, so I'd shade towards it if it's true, so I'm going to shade this little area. So here is our, what we'd call a feasible region. We found our feasible region. This is about 50% of the work. For this particular problem, all these points inside here would be a solution. But the points that are going to generate your maximum or minimum are going to be the vertices. Here's my first vertice right here. And that vertice is 1, 0. Here's another one. That looks like it's 3, 0. And our one up on top here, that's 1, 1, 2, 3, 4. That's 1, 4. So at those 3 points, we're going to generate either minimums or maximums. And here's how it works. We're going to use the objective function right here. Basically, f of x, y, your x, well, let's just do it this way. Here's your x, y values that we just generated. Over here, you're going to have your function, f of x, y, in this case equals 3x plus y. 3x plus y. This is your objective function where you plug in your points. The first point we're going to plug in is 1, 0. Well, just the function here itself, that's going to give us 3 times 1 plus 0 for the y. Well, that's going to give us a total of 3. Plugging in 3, 0, this point right here, it's going to be plugging 3 in for x, so it's going to be 3 times 3 plus 0 times y, or basically 0 for y. This is going to give us 9. Our last one, 1, 4. 3 times 1 plus 4. Well, that's going to give us a grand total of 7. So our maximum is right here. Maximum value we generated, 9. Our minimum value would be 3. That's what we're looking for here. This is a typical linear programming problem. You have your constraints, your objective function, you graph, and go from there. Okay. Once again, graph the following system of inequalities. We're going to use our objective function again right here. We're not graphing that, we're only going to graph our constraints. So, first of all, x, this top one here, we'll graph in blue. X is less than or equal to 2, that's going to be a vertical line at x equals 1, 2, right through here. It says it's less than or equal to 2, so I'm going to shade to the left. That would be less than for any x value. I'll do this one in green right here. I'll put it up here. 3x minus y is greater than or equal to negative 2. I'm going to solve it for y. I think that's the easiest way to graph it. You could do x and y intercepts, but I'm going to put it in slope intercept form. Remember, that's a negative y is greater than or equal to negative 3x minus 2. I have to divide everything by negative 1. And when I do that, I have to flip my inequality symbol. It's kind of a big deal. Instead of greater than, now it is less than or equal to. Negative divided by a negative here is a positive 3x. Negative 2 divided by negative 1 is a positive 2. So graphing that now, my y-intercept is 2. My slope is 3. Up 1, 2, 3, over 1. Up 1, 2, 3, over 1. So it's 1 up on the graph. If this is 7, this looks like this point would be 2, 8. Anyway, down 1, 2, 3, back 1. Back 1. And there's our line. I got to figure out which side to shade. Do I shade towards the blue line or away from it in this case? Actually, we're looking at the point 0, 0 as our checkpoint. So when I plug in 0 for y, 3 times 0 plus 2, I get 0 is less than or equal to 2. So this is true. So I would shade towards the 0, 0. So you can see it's going to kind of be in this area, somewhere in there. We'll get rid of this right now. Okay. Last one here, I'll graph in red. It's already in slope intercept form, so I don't really have to rewrite it. My y-intercept is negative 2. Looks like my slope is 1 over 1. So up 1 over 1, up 1 over 1. There we go. There's another vertice for our feasible region. Down 1, back 1, down 1, back 1. There's another point. This is also a solid line. If I plug 0, 0 in here to see which side I shade, I'm assuming I shade above it, but you should always check because sometimes your feasible regions aren't what you expect. 0 is greater than or equal to 0 minus 2. Is 0 greater than or equal to negative 2? This is true. So I shade towards 0, 0 right here. So I shade above. So here is our triangular feasible region. All our possible solutions for these constraints. But the main thing is, what are the vertices? Looks like our first vertice here is 2, 0. This one up here, looks like we're over 2 and up 8. That's 2, 8. This one down here, looks like it is over 1, down, over negative 2, 1, 2, 3, negative 4, negative 2, negative 4. So, finding our minimums and maximums, we're going to plug it into this objective function. We're going to plug in our x, y points into, basically this is all we really need to know, 2x minus 3y to generate our minimums and maximums. Okay, so our first point was 2, 0. Over 2, up 0. So 2, plugging in 2 for x, minus 3, plugging in 0 for y. This is going to give us 4. Next one, what do we got? 2, 8. 2 times 2 again for our x, minus 3 times 8. This is 4, 3 times 8 is 24, so it's 4 minus 24. That's going to give us negative 20. Our last point, negative 2, negative 4. Okay, so it's 2 times negative 2 minus 3 times negative 4. So this is basically negative 4 plus 12. Negative 4 plus 12 is going to give us 8. So definitely our minimum is negative 20. and our max is 8. These are kind of the basic skills that you need to do a linear programming problem. Now we're going to delve into application here where we get a word problem. And then there's some steps. It's basically the steps that we just took. But the first step here is we got to define a variable, and we'll do that in the next problem. And write a system of linear inequalities. Here, they already had the linear inequalities written for us. This is kind of one of the harder things. The objective function is you're minimizing and maximizing money usually, so when they start talking about money, that'll be our minimum maximum function. Most of the time, not all the time. Graph the system of inequalities, and that's kind of where we went from there. Find the vertices of your feasible region. Write a linear function to be your objective function or minimum maximum function. Substitute in the vertices and find the minimums and maximums. Okay. So here's our first word problem. Actual application. A receptionist. Hold on a second there. A receptionist for a veterinarian. One of Dolores Alvarez's tasks is to schedule appointments. She allots 20 minutes for a routine office visit. 20 minutes for a routine office visit and 40 minutes for a surgery. We're going to use that in a minute. The veterinarian cannot do more than 6 surgeries per day, so that's going to be an inequality. The office has 7 hours available for appointments. That's maybe going to be another one too. If an office visit costs $55 and most surgeries cost $125, how can she maximize the income for the day? Now here we talked about money a little bit. I'll underline it in green. This is probably going to be our objective function or our minimum maximum function. Okay, the two things they talk about are office visits and surgeries. We'll call the number of office visits X, so that's going to be on the X-axis over here. And the surgeries, number of surgeries Y, and that'll be on the Y-axis over here. Okay? Write a system of inequalities. Okay, one of the basic things we have to get used to is this. If there's no minimum here for number of office visits, it's 0. You cannot have more than, they can't have less, they can't have negative office visits. So I'm going to say this, X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. Those two things are usually what you start out with, unless your numbers can be negative, but in the real world most of the time they can't. The veterinarian cannot do more than 6 surgeries per day. So here's one for Y. I cannot do more than 6 surgeries per day. So Y has to be greater than or equal to 0, but it has to be less than or equal to 6. So we have a little window there. And the last one says the office has 7 hours available for appointments. Okay. Well, they talk about minutes up here for office visits and minutes up here for surgeries. So I'm going to create one inequality, but for the 7 hours that I can have for all my appointments, I'm going to change that to minutes. So there's 60 minutes in an hour, so 7 times 60 is 420. So 420 minutes is what we're going to be working with here. But the first thing I'm going to say is this, 20 minutes for office visits, so that's 20x. That'll be all the minutes for office visits, plus the minutes for surgery, it was 40, so 40y. Now this has to be less than or equal to 420. We can't have more than 7 hours or 420 minutes of office surgery. So right here are our constraints. Okay? Step 3, what do we got here? Graph the system of inequalities. Okay. So we're going to graph these bad boys. Looks like it's broken up by 5s here. 10, 15, 20, 5, 10, and 15. I don't think I have to go any higher than 15 when I graph this. So anyway, the first one here, let's graph x is greater than or equal to 0. X is a vertical line. So basically, right here, and it's greater than or equal to 0, it's going to put it to the right. Y is greater than or equal to 0 is a horizontal line where y is equal to 0, so basically your x-axis is y is greater than or equal to 0. So by doing that, it puts everything here in the first quadrant. We're going to shade in this first quadrant. Y is less than or equal to 6. 1, 2, 3, 4, 5. Right here, 6. But the problem is it's less than 6, so below. So this last inequality is going to kind of seal it in. It's going to be in this tube right in here somewhere where our feasible region is. Let's get rid of this. Okay. This last one, usually I solve for y. I don't think this can make this problem any easier. So I'm going to find my x and y intercepts. You could solve it for y and use slope and y-intercept, but I'm not going to do that in this case. To find my y-intercept, let's find our x-intercept first. You'd plug in 0 for y. So I end up with 20x plus 40 times 0 equals 420. Basically that's 20x equals 420. Divide both sides by 20, and I get 21. So my x-intercept equals 21. I'll put that right here. There's 20. There's 21. My y-intercept is where I'd plug in 0 for x. So, well, 0 times 20 is just 0, so I end up with 40y. I'm just going to say equals 420 because I'm just finding the y-intercept. 40 goes in there. 10, if you divide both sides by 40, y would equal 10.5. So right about here. And then you should get a nice straight edge in there. I'm just going to draw it in there. Where do I shade above or below? I know I shade below here, but just to check it, plug in 0, 0. And that's basically, this side is 0. 0 is less than or equal to 420. This is true, so I shade below it. Now, some people might think it's this triangle up here, but it's not. Your feasible region is below this line, above this line, to the right of x is greater than or equal to 0, and then below the green. So it's this four-sided, looks like a parallel, no, it's not parallelogram, what do you call it? Four-sided object, whatever. And then what do we do now? Once we find our feasible region, find the coordinates of the feasible region. Okay, let's give ourselves a little bit of room here. First one is definitely 0, 0. This one is 21, 0. This one right here, that's easy. That's 0, 6. Over 0, up 6. This one right here, ooh, this one's a little fuzzy. And you're going to have this once in a while. And what you have to do is find those two lines. This first blue line was y is less than or equal to 6. So we're just going to go with y equals 6. Okay? And the green line right here was this 20x plus 40y equals 420. And just solve it like a system, I guess. You know y is going to be 6. So I'm going to do this. I'm going to put a 6 right here. We're trying to find the x value. Well, plug 6 in for y right here, and then you can solve for x. What I mean by that is 20x plus 40 times 6, because you know y is equal to 6, equals 420. So 20x plus 240 equals 420. Subtract 240 from both sides and you get 20x equals, oh, I did it already, 180. And then divide both sides by 20, x equals 9. So 9, 6. Sometimes that point that's out in the feasible region, it's not on the x-axis or the y-axis. That point might be a little bit harder to find. You just can use elimination or substitution with the two lines that form that point to find it. Okay. So, step 5 Write a function to be minimized or maximized. This is your objective function. So f of x comma y equals. So this is kind of where we get into money. So let's go back up here a minute. Right here it says office visits are $55 and surgeries cost $125. So that's how much money they make on each one of those. So you would say your objective function, x is the number of office visits, and it's $55 for each office visit. So that's 55x plus $125 for each surgery, 125y. There's our objective function. Then, last but not least, plug the coordinates of the vertices in, and that's going to give you your step 7, your least amount and your greatest amount. Okay, so let's do that. A little bit of math here. We're going to plug in x comma y values into our objective function. F of x comma y equals 55x plus 125y. Okay, what were they? 0, 0. Well, that's a pretty easy one. 55 times 0 plus 125 times 0 equals 0. That would be like a Sunday when it's not open. So there is that. What is another one? 21 comma 0. So 55 times 21 plus 125 times 0. That is equal to $750. $750. That's just office visits, no surgeries. 06. Let's do that one next. That's 55 times 0 plus 125 times 6. And that is equal to, wait a minute here, that's 750. Sorry, I got it mixed up a little bit. 55 times 21 is actually 1,155. Oops. Hey, even teachers make mistakes. The last one was 9/6. Okay, so 55 times 9 plus 125 times 6, and we get a total of 1,245. So what's our max, what's our min? Well, our minimum is obviously 0. No surgeries, no office appointments, that's it. Our maximum was 9 office visits and 6 surgeries of $1,245. So that's what they would want. This is what you would want on a daily basis, as close to that as possible to maximize the income. Okay, that's it. Now you got your worksheet. End of this Unit 3, and we're off to a quiz. Good luck.